Hi students, welcome to the second session of the chapter Atoms. Before I proceed, I would like to inform all of you that before you go through this video, please go through the previous video and understand the concepts thoroughly. By this time, we know that there are drawbacks of Rutherford's atomic model. To overcome the drawbacks of Rutherford's atomic model, Niels Bohr gave his theory in the form of three postulates. Before we go into the postulates, we need to learn the meaning of quantization and angular momentum. Quantization means discrete or not continuous. To understand the quantization, let us consider quantization of charge. You might have studied about quantization of charge in the first chapter. By this time, we know that charging a body is nothing but the process of adding or removing electrons. If we add an electron to a body, the charge on the body is given by Q is equal to 1e, where E is charge on the electron or electronic charge. If we add another electron to the same body, then charge on the body is given by Q is equal to 2e. Similarly, if we add n number of electrons to the body, then its charge is given by Q is equal to Ne, where n is an integer. This means that charge always exists as the integral multiple of electronic charge. That is, charge is not continuous. In other words, we can say the charge equal to 1.5e or 1.6e or 1.7e simply does not exist. Thus, we can say if a physical quantity takes certain predetermined values but not continuous or arbitrary values, then we say that the physical quantity is quantized. To understand what is angular momentum, let us consider a body revolving along the circumference of a circle of radius r. Let m be the mass of the body and v be its velocity. This body possesses an angular momentum which is the rotational equivalent of linear momentum. That means a moving body which is revolving along the circumference of a circle is going to possess a quantity called angular momentum. It is defined as the moment of momentum of a body. That is, angular momentum is equal to moment of momentum of a body. L is equal to r cross p, where r is radius vector, p is momentum of the body, that is linear momentum. So, if we expand this, L is equal to mvr sin theta. If theta is equal to 90 degree, as in this case, what is theta? Theta is the angle between r and v vectors. So here in this case, theta is equal to 90 degree. If theta is equal to 90 degree, then L is equal to m into v into r. Angular momentum is a vector quantity. Now let us proceed with our present topic. It was Niels Bohr who made certain modifications in Rutherford's atomic model by adding the ideas of the newly developing quantum hypothesis. Bohr in 1913 concluded that the electromagnetic theory could be used in explaining large-scale phenomena, but it could not be applied to the processes at the atomic scale. Bohr combined classical and early quantum concepts and gave his theory in the form of three postulates. This model has its place in the history of quantum mechanics, particularly in explaining the structure of an atom. It has become a milestone since Bohr introduced the revolutionary idea of definite energy orbits for the electrons. One can say that the energy is quantized. This means that only certain orbits with certain radii are allowed. Orbits in between simply do not exist. This is in contrary to the classical picture requiring an accelerating particle to radiate energy. Bohr also introduced the idea of quantization of angular momentum of electrons moving in definite orbits. Thus, it was a semi-classical picture of the structure of atom. Although this behavior may seem strange to our minds that are trained from birth by watching phenomenon in the macroscopic world, this is the way things behave in the strange world of the quantum that holds away at the atomic level. In simple words, we can say that to overcome the drawbacks of Rutherford's atomic model, Bohr made three postulates to explain his atomic model. They are as follows. Bohr's first postulate was that an electron in an atom could revolve in certain stable orbits without the emission of radiant energy. These are called the stationary states of the atom. This is in contrary to the predictions of electromagnetic theory. According to this postulate, each atom has certain definite stable states in which it can exist, and each possible state has definite total energy. This is nothing but quantization of energy of an electron inside the atom. What I mean is that if you consider this as an hydrogen atom, this is the nucleus, this is first orbit of the electron, this is second orbit, third orbit, fourth orbit, and so on. In a hydrogen atom, the energy of the electron in the first stable orbit or stationary orbit is equal to minus 13.6 electron volt. We'll come to know about this energy as we proceed further. But for the time being, please see the energy in the first stable orbit is minus 13.6 electron volt. The next or the second stable orbit is this one. Here, energy of the similar electron in the second stable orbit is minus 3.4 electron volt. Similarly, in the third stable or stationary orbit, energy of the similar electron is minus 1.51 electron volt. The energy states between minus 13.6 electron volt and minus 3.4 electron volt simply does not exist. According to Bohr's first postulate, if an electron is revolving in these orbits, what we called as stationary orbits, then they will not emit energy. This is the meaning of Bohr's first postulate. That is, the electrons are restricted to well-defined orbits. Now, the second postulate. This postulate states that the electron revolves around the nucleus only in those orbits for which the angular momentum is some integral multiple of h by 2 pi, where h is Planck's constant, that is L is equal to nh by 2 pi. Bohr's second postulate defines the stable orbits. Since energy of an electron in an atom is quantized, the quantity relevant to circular motion must also be quantized. For circular motion, angular momentum is a very relevant quantity. Thus, Bohr's second postulate of quantization says that the allowed values of angular momentum are integral multiples of h by 2 pi. Here we can note that h has the dimensions of angular momentum. Thus, we can conclude that the second postulate of Bohr is natural. Now we will move on to the third postulate made by Bohr. The third postulate states that an electron might make a transition from one of its specified non-radiating orbits to another of lower energy. When it does so, a photon is emitted having energy equal to the energy difference between the initial and final states. That is E is equal to EI minus EF. The frequency of the emitted photon is given by the equation h nu is equal to EI minus EF, where EI and EF are the energies of the initial and final states, and EI is greater than EF. H is Planck's constant and nu is the frequency of emitted photon. Now let us try to understand Bohr's third postulate. As we can see here, The energy of the electron is quantized. The electron in the first orbit has a total energy of minus 13.6 electron volt. The similar electron in the second orbit has a total energy equal to minus 3.4 electron volt. What does it mean? This electron, which is revolving in the second stable orbit, can also revolve in the first stable orbit by losing its energy. The energy difference that is lost is emitted in the form of photon. Let us consider that the electron in the second orbit makes transition from second orbit of hydrogen atom of energy minus 3.4 electron volt to the first orbit of energy minus 13.6 electron volt. The energy difference, here we can note that minus 3.4 electron volt is greater than minus 13.6 electron volt. What is the difference between the two energies? The energy difference is minus 3.4 minus of minus 13.6, which is equal to 10.2 electron volt, must be given out by the electron according to the law of conservation of energy. This energy is emitted in the form of photon. This is nothing but Bohr's third postulate. Bohr's postulates tell us two things. The first one is the quantization of energy, and the second one is quantization of angular momentum of the revolving electron. Mathematically, quantization of energy is written like this: h nu is equal to ei minus ef. As E is equal to h nu, and E is nothing but energy difference between the initial and the final states of the electrons. And quantization of angular momentum, as we know, L is equal to mvr, and same L is equal to nh by 2 pi. This is according to Bohr's postulate. Therefore, mvr is equal to nh by 2 pi. Now, I request the students to go through the video number of times for better understanding. This chapter will be continued in the next video. Thanks for watching.